Log on, tune in, find out. Another good idea from Cambridge.
So, thanks for the organizers for inviting me here. First, I want to show that it is 7 past 10. So it's a business pharmaceutical day. I'm not sure I'm very good at business, but we shall see. And I would like to apologize to those who have already heard this talk or something very, very similar, and especially to those who have already heard it several times. It may happen. So this is about using penalized the optimum design for dose finding. So this is the outline, but that's the main thing. So the typical type of model we are going to consider is for Bernoulli type experiments, where we have a success or failure, and we have the probability of success, which is modeled and depends on some parameters, and the probability of success is denoted by eta here. So we are going to estimate these parameters by a maximum likelihood. So we maximize here the log likelihood. The feature information matrix has this form, and here, F is this vector here. So this is just the case where we observe success or failure, and we will have an example where we observe more things than that. Yes, we have efficacy and toxicity, this type of things. But okay, this is the general setting. So what I would like to consider is the following problem, where we want to maximize the information we gain, measured by the log determinant of by the information matrix, under some cost constraint. And the cost is an integral cost, where here small phi is the cost of one observation at a given x. So this is the mean cost for which is computed for the design measure itself. Yes. So what can we say about this problem? Well, this is a concave function of psi. This is linear in psi, so there is no difficulty to write some necessary and sufficient condition for the optimality of psi, but this is not the main thing. What is more interesting is that if we want to solve this, it's not very difficult, because we simply have to consider criteria of this form, yes, and we maximize this for an increasing sequence of lambdas. So how does it work? If you take lambda equals 0, you're constructing a d-optimal experiment. If this satisfies the constraints, it's finished. If it doesn't, you take a larger lambda and try again. Yes? And you will stop at the smallest lambda such that the constraint is satisfied. So in practice, what you do, you use a binary, you use a dichotomy search, yes? So it's very fast and converges very fast to the optimum design. So solving this is not more complicated than solving a sequence of the optimum design problems. So this is fine. Why considering this? But Vladimir and Valery, in a series of papers, have considered the following thing for clinical trials. They relate the cost to the success probability. I mean, the probability of efficacy and no toxicity, for instance. And in this sense, then you can distinguish very clearly the part which is related to the information you will gain from the experiment, which we want to maximize, and the information that you are going to use later on, which is information for the future. So it's something related to a sort of collective ethics, something that you gain from the trial, and also the cost of the trial in terms of individual ethics, in terms of the patients that are enrolled in the trial, because you don't want to give them doses that are non-efficient or toxic. So you have a cost here related to you don't want to give bad doses to the patients enrolled in the trial, and you have the information you gain. And in this way, we make a sort of compromise between the two. So in what follows, I shall consider this type of criteria here, which is parameterized by lambda, and the optimal design measure for this criterion will be denoted by psi star of lambda. And I would like to make 3 remarks here. First, if we write here the integral cost in this way, so if we say that it is 1 divided by p times log of some other cost, psi, then solving this problem is strictly equivalent to maximizing this log determinant here. And it's again equivalent to maximizing the total information when n is the number of patients with the total constraint on the cost of this form. Yes. And why this? Because this is exactly the formulation that was used by Vladimir and Valery. Okay. Okay, later, because I'm already late, so later. And so when I'm choosing a coefficient here, lambda is the same thing as if you put here some power in this function here. Okay. The second remark is that with this formulation, we have an upper bound on the costs related to the optimal experiment. I mean, the cost for the experiment here that maximizes this is bounded by this quantity. So of course it will decrease when lambda increases, and we know that it decreases in this way. So this gives us an easy bound on the total cost. And but having a bound here on this integral cost, in some cases it's not enough, because what you would like is that all the support points of the optimal design have a small cost, have a small cost associated with them. It's not enough that you have a small weight, because having a small weight, it means that for some patients, maybe not a lot of them, but for some patients, you will give a high dose or a dose which is not efficient at all. So what you would like is that all the support points will be close, yes? And if you choose the cost function properly, this can be done. And in fact, what you need is that the cost function should be flat enough around its minimum. And it's possible to do that. You choose some cost function. So then you rank, you assume that your design space is finite, which is the case when you do this type of clinical trials. So you assume that the design space is finite, and you rank the design points by increasing value of the cost. Yes? You take just the first m, you take the first m such that this gives a non-degenerate design. Yes? So the first m point gives a non-degenerate design. And then you define, from your original cost, you define a new cost, which is given by you subtract the minimum cost here, and you raise this to some power q. And this defines you a new integral cost. And then it's possible to show that if you take q large enough and lambda large enough, then the support of the optimum design will just be this first point here. So it's possible to choose cost functions so that all the support points will be concentrated around the cost with minimum value. Okay. So we can give exactly the, I mean, we can give precise values on q and lambda so that this will work, but this is not very important. So here is an example which is taken by this paper by Vladimir and Valery. So it's a case where we observe efficacy and toxicity. We have 11 doses in the interval -3, 3, and the model is the following one. I think it's Koch's model. So we have, for instance, this is probability of efficacy and toxicity. This is efficacy and no toxicity, no efficacy and toxicity, and nothing. Yes. So we have 6 parameters here. This is the first penalty I'm considering. This is the penalty is the inverse of the probability of efficacy and no toxicity. So it looks like that, and you have the 11 doses here, here on the horizontal axis, and this is the cost I'm considering. Yes? And this is the optimum design that we get. So this is lambda, remember? And on vertical axis are the doses. And the width here of the lines correspond to the weight we put on the different doses for the optimal design. So for lambda equals 0, we have the optimal design. So the optimal design is supported here, 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 and here. See? And if you increase lambda, you see that you put more and more weight to the 5th dose, and the 5th dose is the one with minimum cost here. So when you increase lambda, you put more weight here. Yes? But you put more weight here, but you still have some weight on these doses here. Yes? So if you don't want that, for instance, you change the cost. As I said, for instance, you can take this cost now. So the same the trick that I mentioned previously. I put here the power 2. So this one is more flat around the minimum. So the minimum is at the same place, of course, but this is more flat. If you compare to previous one, so this was previous one, this is the new one is in red, so it's more flat. And in this case, this is what you get. So again, lambda equals 0, it's the optimum design, and increase lambda, you see I put more weight. So previously I had some weight here, so now I have no weight here. The problem is the minimum cost is for this point here, and it seems that I have no weight here. But this is simply because lambda was not large enough. If I increase lambda a little bit more, I go to 1000, you see that then I put more and more weight to the central point, yeah, which is the minimum cost. Okay. We can even decide to put more stress on avoiding toxic doses. So here we have a cost that gives more importance to toxicity avoidance. So this is the cost here. We multiplied the first one I had by this thing, which is the inverse of the probability of toxicity. And then the new cost function looks like that. And if you compare to previous ones, you see that, okay, so the new one is the purple one here. You see we put more stress on avoiding toxicity. And then we have this type of behavior. And now you see that for lambda large enough, all the doses are concentrated on the fourth and the fifth one. Okay, but now now the minimum cost is obtained for the fourth one, not for the fifth one. But so you see, if we play with different, if we play with the cost function, if we play with lambda, we can tune the type of design that we get. Okay. Now, the next idea is to implement this in a sequential construction, because these designs you need to know the value of the parameters to construct them, because the model is nonlinear. So because the model is nonlinear, we're going to use sequential design. So this is a standard situation in nonlinear models. We know, for instance, here for a nonlinear regression model, we know that the model is nonlinear, so the derivative of the response with respect to the parameters depends on the parameters, so the information matrix depends on the parameters, so you need to know the value of the parameters. So to avoid that, we use sequential design. So here, full sequential design and the optimal design, for instance, because this is the simplest thing we can present here. So we start by some points that are chosen, and then we start to observe, estimate, choose next design point, observe, estimate, and so on. So next design point is chosen to maximize the determinant of the next information matrix, which is the same thing as maximizing this quantity here. So we can use that. How are we sure that it will work? I mean, we did converge to something, and to what? So it's not easy, because the fact that we choose this design point, you see this design point here depends on the current estimated value of the model parameters, which means that you will observe at a point that depends on the value of previous observations. So the independency is lost, and because you lose independency, then it's difficult to show that the estimator is consistent, and it's even more difficult to show that you will have asymptotic normality, because this matrix here is a random matrix. It's not the information matrix, because each point here, xi, is random, because it depends on the estimated value. So it's okay. These type of things are difficult to prove, but here we are in a in clinical trials we are in a rather favorable situation, because the number of doses is finite, so the design space is finite. And if the design space is finite, necessarily you will observe infinitely often at some doses. And this helps very much to prove all the properties. So all what we need, in fact, is that here, the sum of squares of differences of responses or of probability of success at two different values of theta grows fast enough when the two values of theta are different. This is all what we need. And in fact, the growth rate we require is not very big, because we simply need this to grow faster than log n. So it's
I don't understand the condition. So the summation index is k,
It's I, sorry.
So it's I.
Yeah. K is I in my standard. No, sorry for that, yes.
Yeah,
it's
no,
I.
it's-
It's
Although
I.
it's also okay, but it's always satisfying.
Okay.
Yeah,
Okay. So this is all what you need here, and even for it's also easier for asymptotic normality, because then all what we need is a property similar in the sense that we need the consistency of the estimator, but then what we need is to be able to renormalize the sequence of matrices, which is a sequence of random matrices. We need to be able to renormalize it by a deterministic sequence of matrices. And if we do that, then we have asymptotic normality. And if we apply that to a sequential d-optimal design, so this is the sequential construction that we have. First, using the fact that the design space is finite, we can show that whatever the value of the theta k that we choose, not necessarily the estimated value, you can plug it any sequence of random or deterministic values here. You will always sample your finite design space. You will always sample a non-singular design with some sample rate, in the sense that there is a subset of the design space, a subset that forms a non-degenerate design, which is sampled at a frequency strictly positive. And using this, then from the theorem from before, we can easily show that the estimator is consistent, and then by some continuity argument, the matrix will tend to the optimal matrix, and because it tends to some constant matrix, we can renormalize this one by the constant matrix, and then we get asymptotic normality. Okay. Now, we can do exactly the same when we have penalized the optimum design. Simply the construction, instead of having just this term, now we have also this penalty here. Again, because we do sequentially, the independency is lost and so on. But if the design space is finite, we get the same type of result. If lambda here is constant, then we get that the estimator is strongly consistent. The matrix tends to the optimal matrix for this problem here, and the parameters are asymptotically normally distributed. It's not absolutely required to take lambda equal to a constant. For instance, instead of having lambda equal constant, you may decide to solve the constraint problem, where you maximize this under this constraint. Yes. If you do that, because you do that at each step for a different theta k, so the Lagrange coefficient at each step will depend on theta k. So it's not constant, but it's a measurable function of all the past, and this still works in this case. And in this case, you will converge to the optimum design for this constraint design problem. So this is what you get if lambda is bounded. Even more interestingly, you can let lambda tend to infinity. So if lambda increases to infinity but not too fast, then we still have the strong consistency of the estimator, and moreover, the average cost will tend to the minimum cost. Yes, and which means that the weight, the total weight we are giving to the point where the cost is minimum, if there is a unique minimum, this weight tends to 1. And if you have chosen a suitable cost, all the design points will tend to concentrate around the point of minimum cost. Which means that we can optimize a function like this without knowing the value of the parameters, which is called self-tuning optimization. We simply have to use such a construction. And this had already been suggested in the literature on adaptive control, but just for the case where for a sort of linear regression model, and okay, no conditions on the choice of lambda k was given, and so on. But so here we have something that works even when the model is nonlinear and so on, but we have this condition that the design space is finite, which is not very restrictive for those studies, because the number of doses is usually finite. And of course, for this type of problems, if you use the best intention design, it will, in general, this doesn't work. Okay, so I will skip this example and go directly to this one. Oh, still have some time, yes. So I'm back to the example I presented previously. So we have 11 doses, you remember, we observe efficacy and toxicity. We shall compare to an up and down method where we decrease the dose if we observe toxicity. We stay at the same dose if we observe efficacy and no toxicity, and we increase the dose if there is nothing, if there is no response. So we will apply that for all the trial, or we shall apply that just for the 10 first patients and then switch to some sequential rule. For instance, if we switch to the sequential penalized de-optimum design rule, this is a typical behavior that we have. So up to the 10th patients, we have this up and down, and we switch when we observe a toxicity for the first time. So this is here, we observe toxicity for the first time, and then we switch to this adaptive rule. So this is, okay, this is so what it does. You see it goes to rather high doses. But this is related to the penalty that we use. The penalty is simply related to efficacy and no toxicity. If we want to avoid high doses, we need to penalize more the presence of high doses, and we can use this penalty now, where I also penalize simply for toxicity. And then on the same trial, this is what we had, and this is what we get now. You see, we switch at the same point, 10, first toxicity is observed, and then we have this. And then we avoid the high doses. So this is the typical behavior that we have. Now, if we compare to other methods, so what do we have here? So this is a cost for the cost which is related to efficacy and no toxicity. The criterion J is related to the uncertainty on the estimation of the parameters. So we want both of them to be small. And this tells after one trial, so each trial has 36 patients, we have done 1,000 repetitions, and for each trial where we estimate the optimal safe dose. Yes? So the optimal safe dose is the fifth one in the simulation. So where we estimate the fifth dose. So the first strategy is simply the up and down method. We use up and down for the 36 patients. The second sequential strategy is when you use first up and down and then sequential de-optimal. And the last one is when you use first up and down and then sequential penalized de-optimal. And you see that, of course, in terms of estimation, the best is when you use the second one. For instance, you find in more than 70% of the cases, you locate the optimal safe dose. But you see that, but here the cost is rather high if you compare to the cost of the up and down method. Now, if you use up and down followed by sequential penalized the optimal design, you can see that you remain rather good in terms of the location of the optimal safe dose, in terms of the precision of all the parameters, the estimation of all the parameters of the model, and the cost is now much smaller than the cost for the de-optimal experiment. It's higher, of course, than for the up and down, but it's reasonable. Okay, we can even do that now. If we consider a longer trial, so it's a very long trial with 240 patients, but the trial is so long that we can think that it is interesting then to construct a non-stationary experiment, in the sense that because we are learning in the course of the trial, then we can try to give at the end of the trial to give doses that are closer to the optimal safe dose. And we can do that by letting the penalty coefficient here, lambda n, increase with n. And if it increases here with a logarithmic scale, this is the type of behavior that we have. So you see that in this case, of course, the trials are longer, so we get better results. But you see that in 90% of the cases, we locate the optimal safe dose. So it's much better than the up and down method. in terms of precision, we do better than the up and down method, and we also do better in terms of cost. Because if lambda increases, the patients at the end of the trial will receive more and more doses that are equal or close to the optimal safe dose. Okay, so this just 2 slides for the conclusion. So there are still much things to be done here, but I think that the idea of having a clear formulation of a criterion where you have 2 parts, one part related to the information you gain from the experiment and one part related to the cost of the experiment. And in any case, you always need to combine that. And it seems to me that very often this is combined, but not so clearly. I mean, you don't know exactly how it is combined, but it is always combined when you do this type of trial. So here, at least we know exactly how we combine the things, and we have a tuning parameters that sets that will say what is more important for us in this trial, in this particular trial. So I think this can be something useful for this type of experiments. And now in terms of theoretical issues, we have some consistency and asymptotic normality results, but I always use this assumption that the design space is finite, so it's not very restrictive here, but in other circumstances it could be restrictive, so it would be interesting to see if we can bypass this type of assumptions. So we know that if here lambda tends to infinity, not too fast, so everything is fine. We will converge to the minimum possible cost and so on. About asymptotic normality, we need to be able to renormalize the information matrix by a sequence of deterministic sequence of matrices. And if lambda is tending to infinity, it's not obvious to decide which type of sequence of matrices we should consider. So this, for me, this is still an open issue, and that's all. Thank you very much.
Thank you very much. As promised, very interesting theoretical findings and methodology. So questions? Alessandra.
At one point you have a number of points where you have to put a positive frequency of observations. Is that number the same as the number of parameters?
You mean here?
Yeah.
This one. Well, it's not that you have to. It's the fact that when you construct an experiment like this, by sequential de-optimization, this will be done automatically.
Okay.
So it's not you who decides. It's done automatically. The construction itself will do that. And if you use penalized design, then you will not have this, but you will have this multiplied by lambda. You will have, because if you use a penalized design, and if lambda is increasing to infinity, here you will have this multiplied by lambda.
The extreme.
And this is why if lambda grows to infinity but slowly enough, then it will still work and you will still have consistency.
Yes.
Say if you were by your penalty function phi, how you choose in general?
Well, here it's I don't say it's easy, but you will tend to relate this to here to the efficacy, non-toxicity, and so on. So in this type of problems, there are some intuitive ways how to choose phi. Yes, but then for instance, this phi, I mean this red curve here and the blue curve, which is simply this part here, they have the minimum at the same point, but one is more flat than the other.
Would that be the case? You choose the wrong penalty function to work with?
Well,
you can choose wrong client as well. So
But in what sense wrong?
Well, what sense is right?
Depends on the objective of your study. What do you want to learn with that study? So that's how you build the cost function. Yes. Sorry, you were first.
Okay. Next plot.
next one.
Nice plot.
No, can you show the next one? Yeah. This looks to me like it's like a minimal support 2-point design at the end, but with 2 sets of clusters of points. And it makes
Good.
me think
Is
that
this
a
one?
criticism of optimal designs is that they're usually minimal support.
Yes.
But if you apply your approach, then you could come up with alternative designs which have got 2 sets of points, each clustered around what might be a minimal support.
I mean, I cannot predict for each value of lambda how many support points you have. This is difficult. But we know for lambda equals 0 because this is the optimal, we can compute. And we know when lambda is large enough, we know.
But what I'm thinking is that maybe this approach could be used to avoid minimal support designs in a traditional setting.
But Ben, those are weights, I think, on the vertical axis.
Yes, this the height is
The weight is a weight, yes?
Yes. Yeah.
This is almost
So it's a design.
approximately
Two
same
support
weight.
points, yeah.
This is 2 support points, yes.
The last question, please.
Yes, thank you, Luc. I have 2 questions. First, I assume that you can easily extend that to, I don't know if you said that group sequential, well, you have a cohort at each.
Yes, it's
time.
easier. But it's
Okay. And the other thing is, I was thinking, is there any way to incorporate the imprecision on TTK at? You know, because you do fitting, you have its observed fission function metrics, so that it's more or less. Then we're going more or less to pseudo Bayesian design, but instead of-
yes. For instance, here you mean okay, this is sequential.
yes, when you
optimal design.
estimate TTK plus 1, you use the imprecision in TTK.
You would like to put an expectation here, yes?
Yes, something. Did
Yeah,
you?
can, yeah.
Okay, thank you again. So now.